Welcome to For Science Salah Lotfy channel. Today we explore a scientific breakthrough that could reshape the future of quantum technologies, the creation of the world's first photonic supersolid. Imagine a material that combines the rigid, ordered structure of a crystal with the frictionless flow of a superfluid. This strange and counterintuitive state of matter is called a supersolid. For decades it remained a theoretical curiosity, glimpsed only in ultra-cold atomic gases under extremely delicate conditions. But now, a team of researchers has achieved something unprecedented. They created a supersolid made of light itself, inside a photonic crystal waveguide. Here's how they did it. The scientists condensed polaritons, hybrid particles that blend the properties of light and matter, inside a specially designed photonic crystal. By shining laser light and cooling the system close to absolute zero, they observed the spontaneous formation of a new quantum phase. This phase showed two remarkable traits: a crystalline modulation, meaning light organized itself into a repeating pattern, just like atoms in a solid, and at the same time, superfluid behavior, allowing the system to flow without viscosity. It was the first direct evidence that supersolidity can exist in an optical platform. The importance of this discovery goes far beyond physics curiosity. For the first time, researchers demonstrated supersolidity in a non-equilibrium, photonic environment, which is far easier to engineer than atomic systems. This means scientists now have a new and powerful laboratory to explore quantum collective behaviors, from phonon-like excitations to Goldstone modes, phenomena that were previously accessible only in ultra-cold matter. On the technological front, the implications are enormous. Supersolid light could provide novel building blocks for quantum computing, where photons replace electrons. It could enhance advanced photonic circuits, enabling programmable quantum simulators. And because the platform is built using nanofabricated photonic crystals, it is inherently scalable and industrially viable. Economically, this breakthrough could accelerate the development of quantum communication networks, high-efficiency optical processors, and even new energy-saving devices that exploit frictionless light transport. What makes it especially exciting is that these systems do not require the enormous infrastructures of cold atom laboratories. They can, in principle, be integrated into solid-state chips, paving the way for a new era of quantum technologies. This discovery marks a milestone in the marriage of light and matter. Supersolid light is no longer a dream, it's a reality, and it could transform the technologies of tomorrow. To explore the full research and dive deeper into the science, join us only on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. In today's episode, we explore a remarkable scientific achievement recently published in Nature, research that marks the first experimental realization of supersolidity in a photonic crystal waveguide. Supersolidity is one of the strangest and most fascinating phases of matter. It combines two seemingly opposite properties, the rigidity of a crystal and the frictionless flow of a superfluid. For decades, physicists wondered whether such a state could exist in light-based systems. This new research provides the answer, and the result is groundbreaking. The study is titled, Emerging Supersolidity from a Polariton Condensate in a Photonic Crystal Waveguide. It was published in Nature, volume 639, issue 8054, dated July 3, 2024, with the official publication date on March 13, 2025. This international collaboration brought together brilliant minds from leading research institutions around the world, Dr. Dimitrios Tripojorgos and Dr. Antonio Gianfrade, from CNR Nanotech, Institute of Nanotechnology, Lecce, Italy. Dr. Manuele Landini from the Institute für Experimental Physik und Zentrum für Quantenphysik, Universität Innsbruck, Austria, Dr. Davide Nigro and Dr. Dario Garace from the Department of Physics, University of Pavia, Italy, Dr. Jacopo Carosotto from the Pitevsky BC Center, CNR Eno and the University of Trento, Italy, Dr. Fabrizio Rimanucci from the Molecular Foundry, Lawrence Berkeley National Laboratory, USA, Kirk W. Baldwin and Dr. Lauren N. Pfeiffer from PRISM, Princeton University, USA, Dr. Giovanni Nunmartone, affiliated with CNR Nanotech and INFN Lecce, Italy, Dr. Milena De Giorgi, Dr. Dario Ballerini, and Dr. Daniele Sanvito, also from CNR Nanotech Lecce, Italy. Together, their combined expertise in nanotechnology, photonics, and condensed matter physics made this discovery possible. The researchers used a photonic crystal waveguide, a finely engineered structure made with nanofabrication techniques. Within this waveguide, they condensed polaritons, hybrid particles that emerge when light strongly couples with matter. When the system was pumped with laser pulses and cooled near absolute zero, something extraordinary happened. The polariton condensate formed a crystalline modulation, showing periodic order like a solid. Simultaneously, it maintained superfluid flow with no viscosity, a hallmark of quantum liquids. This achievement is not just a scientific curiosity. It demonstrates that supersolidity can exist in a non-equilibrium, light-based system, which is far easier to fabricate and control than ultra-cold atomic setups. It opens the door to exploring exotic quantum behaviors such as phonon-like excitations, Goldstone modes, and multi-mode quantum dynamics, all within a photonic chip. The implications are vast, developing photonic quantum simulators to study complex quantum systems. Building quantum computing platforms where light, not electrons, is the foundation of processing, creating advanced optical circuits with unique supersolid properties. This study, led by researchers across Italy, Austria, the United States, and beyond, marks a milestone in quantum science. Supersolid light is no longer a theory, it's a reality. For a closer look at this groundbreaking research, stay with us on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In this episode, we journey into one of the most exotic phases of matter ever imagined, the supersolid. A supersolid is a counterintuitive phase of matter. Its particles arrange themselves into a crystalline structure, just like atoms in a solid. Yet at the same time, these particles are able to flow freely without friction, a property of superfluids. To achieve this remarkable duality, the system must share a global macroscopic phase while lowering its energy through spontaneous self-organization. For more than 50 years, physicists speculated about the possibility of this strange state. Supersolidity was glimpsed in ultra-cold atomic systems, particularly Bose-Einstein condensates. There, different mechanisms were used to create it. Atoms coupled to electromagnetic cavities, spin-orbit interactions, or strong dipolar forces. But these approaches required complex and costly infrastructures, limiting their practical applications. Now, a new path has opened. For the first time, scientists provide experimental evidence of a supersolid phase in a photonic platform, specifically a condensate of exciton polaritons inside a patterned photonic crystal waveguide. This is not an equilibrium atomic gas, it is a driven dissipative system based on light and matter, forming polaritons with exceptionally low losses. In this experiment, polaritons condensed into a bound in the continuum state, a special optical mode that suppresses losses and enhances coherence. The researchers measured density modulations in the polariton condensate, proving the breaking of translational symmetry, local coherence of the superfluid component, confirming the coexistence of crystalline order and frictionless flow. These measurements revealed the supersolid's dual nature with unprecedented precision, down to a few parts in 1,000. At the mean field level, supersolidity can be understood as two-mode condensation. In a normal condensate, only one mode dominates, breaking asymmetry and giving rise to superfluidity. But in a supersolid, an additional mode at finite momentum becomes populated. This breaks translational symmetry and produces a repeating density pattern. This process introduces new collective excitations, a Goldstone mode, related to shifts in the density pattern, and a Higgs mode, connected to changes in the amplitude of the modulation. Unlike atomic systems, this photonic approach offers several unique advantages. 1. Extremely low losses that lower the threshold for condensation. 2. Negative effective mass, which makes the polariton state self-localized. 3. And a clean, controlled environment with no competing lower energy states. Together, these features make the supersolid behavior clearly visible and much easier to study. This discovery represents a milestone in physics. It not only confirms that supersolidity can exist beyond ultra-cold atoms, but also introduces a synthetic photonic material capable of hosting phonon dynamics and a multi-mode excitation spectrum. The implications are profound. Quantum simulations using light-based supersolids, next-generation photonic circuits that merge coherence with crystalline order, and potentially, quantum processors and communication devices based on photons instead of electrons. Supersolidity was once a theoretical dream. Today it has been realized in a new photonic platform, opening doors to technologies we can only begin to imagine. For more insights into this fascinating discovery, stay with us on For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. In today's episode, we continue exploring the remarkable discovery of a photonic supersolid, focusing on one of its most fascinating features, how coherence and collective dynamics emerge in this exotic state of light and matter. To understand a supersolid, it's not enough to see density modulations or crystal-like patterns. We must also prove that coherence, the delicate quantum order, is preserved across the entire system. In this experiment, researchers used advanced interferometric techniques to measure both local and global coherence of the polariton condensate. By capturing the full wave function through off-axis holography, they could directly map the microscopic spatial correlations of the system. Above the condensation threshold, the measurements showed that the wave function remained fully coherent. But here's the intriguing part. The amplitude of coherence was modulated, and these modulations aligned with the supersolid's crystalline density pattern. This means that even though the system broke translational symmetry and formed a periodic structure, its superfluid character survived, a true hallmark of supersolidity. The team then examined long-range order by analyzing interference patterns. These revealed how different momentum components, the pump, signal, and idler modes, remained phase-locked with one another. This established that both diagonal and off-diagonal long-range coherence exists simultaneously, the crystalline order of a solid, and the global phase coherence of a superfluid. Together they confirmed the system was not just partially ordered, but a genuine supersolid of light. But the story doesn't end there. Another striking observation was the non-rigidity of the density modulation. In many cavity-based supersolid systems, the modulation wavelength is fixed by the cavity geometry. But here, in the polariton condensate, the modulation was dynamic. It shifted as the pump power increased. The wave vector of the modulation adjusted itself due to polariton-polariton interactions and energy blue shifts. This behavior is reminiscent of a roton-like mode, a collective excitation where the system flexibly adapts its periodic structure. This flexibility is more than a curiosity. It shows that the photonic supersolid can host collective excitations, such as phonons and roton-like modes. These excitations determine how the system responds to external forces and provide a powerful platform to study quantum many-body physics in a new regime. Unlike fixed cavity systems, this photonic platform offers the freedom to probe and manipulate these modes, bringing us closer to a controllable quantum laboratory on a chip. By proving that both local coherence and global long-range order coexist, and by observing the non-rigidity of the modulation, researchers have shown that this photonic supersolid is not just a static curiosity. It is a living, dynamic quantum state. A new frontier of light and matter is unfolding before us. For more in-depth explorations of groundbreaking discoveries, stay tuned to For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today we conclude our deep dive into one of the most fascinating breakthroughs in modern physics, the experimental realization of a supersolid phase of light and matter inside a polaritonic system. This part of our journey focuses on the discussion and outlook, exploring not only what the researchers found but also what these discoveries mean for the future of science and technology. To recap, a supersolid is an exotic phase of matter where a system behaves like both a solid and a superfluid at the same time. In this study, the team demonstrated a photonic supersolid using a polariton condensate inside a specially engineered photonic crystal waveguide. Unlike traditional atomic systems which require ultra-cold temperatures and delicate cavity setups, this platform offers a novel, flexible, and highly tunable environment to explore supersolid physics. The researchers carefully characterized the system in both coordinate space and reciprocal space. They showed the formation of crystalline density modulations, proving the breaking of translational symmetry, the coexistence of long-range diagonal and off-diagonal order, confirming global coherence, and interaction-dependent behavior, where the modulation and properties of the supersolid varied with the strength of polariton-polariton interactions. This was not just an analog of atomic supersolids, it was a completely new mechanism, unique to driven dissipative non-equilibrium photonic systems. Central to this discovery was the optical parametric oscillation, OPO process, which spontaneously broke the symmetry of the condensate. The experiment revealed two distinct thresholds. 1. At the first threshold, the polariton condensate formed. 2. At higher power, the OPO process activated, driving the system into the supersolid phase. This dual threshold behavior reflects the rich nonlinear dynamics at play, setting photonic supersolids apart from their atomic cousins. One of the most exciting aspects of this platform is its engineering flexibility. By exploiting the properties of photonic crystals, it is possible to reduce or even eliminate unwanted couplings between modes. For example, using TE and TM polarized modes, researchers could access a regime of full phase freedom in the density modulation. This means future experiments may probe higher-order coherence functions and even capture single-shot realizations of supersolid behavior, something impossible in large atomic setups. Because the crystalline modulation is not rigid but influenced by short-range polariton interactions, the supersolid hosts a non-rigid lattice structure. This opens the door to observing two goldstone branches in its low-energy excitation spectrum, corresponding to the broken symmetries of superfluidity and crystallinity. In practical terms, this means the system can sustain phonon-like excitations, much like vibrations in a real crystal, and roton-like modes, where the modulation wavelength shifts dynamically with power. Such collective excitations are the fingerprints of quantum many-body systems, and studying them in a photonic platform is unprecedented. So where do we go from here? The researchers envision several exciting directions: higher dimensional systems where new rotational symmetries could break, giving rise to complex vortex dynamics, dipolar interactions engineered by coupling to indirect excitons, which could stabilize new types of crystalline phases, and even hybrid Bose-Fermi mixtures where excitons interact with electron gases, opening the door to supersolidity and mixed quantum fluids. Each of these directions expands the horizon of what's possible in quantum photonics. Beyond pure science, the technological implications are profound. A controllable chip-scale supersolid of light could enable neuromorphic computing architectures inspired by the way the brain processes information, quantum simulators capable of modeling materials and processes that are impossible to study otherwise, and photon-based quantum processors where coherence and crystalline order provide stability and scalability. Because these systems are built on semiconductor platforms, they are inherently scalable and integrable into future quantum technologies. This work was made possible by an international collaboration spanning Italy, Austria, the United States, and beyond. It was supported by European and American funding agencies, highlighting how global cooperation drives progress in frontier science. In summary, the demonstration of a supersolid polaritonic system is not just a milestone in quantum physics. It's a stepping stone to new quantum materials, novel computing platforms, and revolutionary photonic technologies. Supersolidity, once a theoretical dream, is now a tangible reality, and its brightest applications are still to come. Thank you for joining us in this deep exploration. Stay curious, and stay with us on For Science Salah Lotfy channel. Welcome back to For Science Salah Lotfy channel. In the final part of our exploration into the discovery of emerging supersolidity and polariton condensates, we turn our attention to the supplementary information, the technical backbone that gives depth and precision to the main results. This section may seem complex, but it holds the key to understanding how the researchers validated their observations and ruled out alternative explanations. Let's break it down. At the heart of this study lies the dispersion of the photonic crystal waveguide. The team represented the system using an 8x8 Hamiltonian matrix, capturing the interactions between different propagating modes, the fundamental TEO and higher-order TE1 modes, along with the exciton resonance. By setting the bare exciton energy as the reference, they could map how the coupled modes evolve in momentum space. This block structure simplifies into smaller subsystems, a 2x2 spin-like system describing the photonic part of the bound state in the continuum, or BIC, and a block describing the co- and counterpropagating TE1 modes, which define the periodicity of the supersolid. This mathematical foundation ensured that the observed supersolid was not an artifact, but a robust physical reality. Next, the researchers probed the system through resonant excitation of the TE+1 modes at the BIC energy. When two laser spots were injected resonantly, they interfered to form a striking optical lattice structure. What's remarkable is that the interference fringes had twice the spatial frequency compared to the supersolid observed in non-resonant conditions. This confirmed that the solid part of the polaritonic supersolid could be isolated and studied independently. It also provided direct evidence of crystalline modulation, free from noise introduced by the excitation laser. But there's a deeper question. If this is truly a spontaneous phase transition, why do we consistently observe the breaking of translational symmetry? The answer lies in linear coupling between the modes, which acts like a built-in symmetry-breaking term. In theory, an infinite system with vanishing coupling would restore full phase freedom. But in practice, the waveguide has finite length, 300 microns in this study, and the pump power introduces nonlinear effects. Interestingly, even when the team tested longer waveguides of 1 millimeter, the results were the same, showing that standing wave artifacts were not responsible. This is crucial. It means the observed supersolid modulation is intrinsic, not an artifact of the device geometry. Another fascinating detail comes from spatial and transverse phase fluctuations. When the excitation spot was shifted along the waveguide, the density modulation acquired a smooth phase shift, proportional to the displacement. In the transverse direction, the researchers observed that at low power, the modulation phase was completely random, consistent with an incoherent state. But as the pump power increased beyond threshold, the distribution narrowed, stabilizing into a coherent supersolid. This smooth transition from randomness to order is a hallmark of spontaneous symmetry breaking. The team went further by averaging over 50 realizations of the condensate. Below threshold, phase fluctuations were broad and random. But as the pump crossed 1.5 times the condensation threshold, the fluctuations reduced significantly, showing the emergence of long-range order. This statistical validation reinforces that the observed supersolid is not a rare event, but a reproducible quantum phase of matter. Finally, to refine their measurements, the researchers used holographic imaging techniques. The challenge was that the excitation laser created a bright exciton reservoir, adding unwanted background emission. By applying interferometric filtering, they were able to remove this incoherent contribution. The result was a clear, realistic representation of the supersolid density in both coordinate and reciprocal space. This level of precision imaging is vital. It allows physicists to separate true quantum order from experimental noise. And so, through careful mathematical modeling, resonant probing, phase analysis, and advanced imaging, the researchers confirmed beyond doubt that they had created a supersolid polaritonic system. This achievement not only advances our understanding of exotic phases of matter, but also lays the foundation for scalable photonic platforms that could one day power quantum simulators, neuromorphic processors, and next-generation optical technologies. From theory to experiment, from noise to order, this study represents the very essence of scientific discovery. Thank you for joining us on this journey. Stay curious, and stay tuned for more explorations here on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel. I am Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority. Today, on behalf of both myself and this channel, I would like to extend my sincere thanks and deep appreciation to a remarkable group of international researchers whose work has greatly contributed to the advancement of science. We would like to express our gratitude to Dr. Dimitrios Tripogiorgos, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy; Dr. Antonio Gianfrede, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy; Dr. Manuele Landini, Institute für Experimental Physik and Center for Quantum Physics, University of Innsbruck, Austria; Dr. Davide Nigro, Department of Physics, University of Pavia, Italy; Dr. Dario Garas, Department of Physics, University of Pavia, Italy; Dr. Jacopo Carusotto, Pitevsky Beck Center, CNRNO and Department of Physics, University of Trento, Italy; Dr. Fabrizio Riminucci, postdoctoral researcher, Molecular Foundry, Lawrence Berkeley National Laboratory, USA; Dr. Kirk W. Baldwin, Senior Research Specialist, PRISM, Princeton University, USA; Dr. Lauren N. Pfeiffer, Senior Research Scholar in Electrical and Computer Engineering, PRISM, Princeton University, USA. Dr. Giovanni Agnes Martone, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy, and INFN, Sezione de Lecce, Italy. Dr. Milena De Giorgi, Technologist Director, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy. Dr. Dario Ballerini, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy. Dr. Daniele Sanvito, CNR Nanotech, Institute of Nanotechnology, Lecce, Italy. Each of these researchers has played a vital role in expanding our understanding of fundamental physics, quantum systems, and photonic technologies. Their combined efforts have advanced not only science itself, but also the technological possibilities of the future. I also want to take this opportunity to thank you, our valued viewers and followers of For Science Salah Lotfy channel. Your support and interaction inspire us to highlight global research and bring it closer to you. I warmly invite you to share your thoughts and comments about this research below the video. Your reflections and questions will enrich the scientific dialogue we aim to build here. On behalf of For Science, Salah Lotfy channel and myself, Professor Dr. Salah Lotfy, I extend my heartfelt appreciation once again to these outstanding scientists, and to all of you for being part of this journey of knowledge and discovery. Stay connected, stay curious, and thank you for watching.